Okay, so we previously discussed the snap problem. So we wanted to know what was the probability of that a game of snap will run all the way through to the end. We were playing snap with a pack of 16 cards. And as we explained previously, what the key point here is that we need to know the number of ways of placing 16 non-challenging rooks on a board like this. So this is a 16 by 16 board, mostly white, except that we've got these 4 by 4 blocks along the diagonal, and there's 4 of these blocks. Okay. So we need to calculate the number of complete rook placements for this board. And we're going to do that using the inclusion-exclusion principle for rook polynomials. So what we need to, so for that we need to calculate the rook polynomial for the black part of the board and then apply the appropriate formula. So to calculate the rook polynomial for the black part of the board, we need to do some kind of calculations expanding out polynomials of rather high degree, and we were quite strenuous to do that by hand. So the purpose of this demonstration is just to explain how you can do those kinds of calculations using a computer, either using Python or using Maple. Okay, so firstly we'll do this in Python. Okay, so here we've got, this is a web page where you can use Python online, Python with the SymPy library. The SymPy library is used for symbolic calculations, so that's an appropriate thing to use if we want to work with polynomials. So the first thing we do is do x is symbols x. That tells SymPy that we're going to just treat x as a symbol rather than an actual number, and we're going to do polynomials in x. Okay, so now we want the rook polynomial for one of the 4 by 4 black squares, so we're going to call that p. Okay. Okay, so so that's just a 4 by 4 square with it's an empty square, so we had a standard formula for that. It was the sum of 4 choose k squared times k factorial times x to the k, with k running from 0 to 4. Okay, so the Python notation for that. So we have sum map lambda k, and then now we have to write the formula, binomial 4k, and then we have to write a star for multiplication. Oh no, we have to, firstly we need to raise this to the power 2. So star star is Python notation for raising to a power. And then we have to multiply by k factorial. So Python notation for k factorial is factorial k. And then we need to multiply by x to the power k. So again, remember star star for raising to a power. And then we have to write range 5 here. Okay, so in Python, range 5 means the numbers 0 up to 4. Okay, so we're taking a sum from k as 0 to 4. So what we're doing, we're taking range 5, which is the sequence 0 up to 4. We're applying this function to it, so we replace k by 4 choose k squared, k factorial x to the k, and then we add them all up. So we've set p to be equal to this polynomial, but the way Python works, it won't just tell us the answer. We have to ask it separately to tell us the answer. Again, this is what it is. 1 plus 16x plus 72x squared plus 96x cubed plus 24x to the 4th. Okay. So now we need the rook polynomial not just for one of these 4 by 4 black squares, but for all 4 of them. So for that we just need to raise p to the power 4. And then we want to expand it as well. So here's the answer. It's a polynomial of degree 16, starts 1 plus 64x, 1824x squared, and ends up with this big number, about 300,000 times x to the 16. Now we need to use the inclusion-exclusion principle for rook polynomials, and that tells us that the total number of full rook placements on the white part of our snap board is like this. We have to take the sum minus 1 to the k, 16 minus k factorial, times the coefficient of x to the k in this polynomial r that we've just worked out. So that's so the appropriate syntax is like this: sum map lambda k, and then we have minus 1 raised to the power k. times 16 minus k factorial, and then you write r dot coef xk as the coefficient of x to the k and r, and then again we're doing this the sum from 0 to 16, so range 17 is 0 up to 16 in Python notation. Okay. So here's our n, and so yeah, we could count the digits, but it's better if we just do n dot eval f. Okay, this will kind of convert it to scientific notation, and we see oh, that didn't quite work how I was expecting it to. Yeah, so I guess we do have to count the digits: 1 2 3 4 5 6 7 8 9 10 11 12, so it's about 10 to the 12. Okay. But we're actually more interested in not just the number n itself, but we wanted to know the probability of completing a game. So for that we had to divide by the total number of of possible replacements on the whole board, which was 16 factorial. Okay, so that ends up being a 0.0118, or in other words about 1.18% is the probability of completing this 16 by 16 game. Okay, so that's how we did it in Python, and we'll quickly do it in Maple as well. Okay, so but actually in Maple we'll do the 52 by 52 version. Okay, so again, so here we're going to have slightly different notation. So in Maple we can use notation that's a bit closer, in fact, to ordinary mathematical notation. So yeah, so here we write add instead of sum, but it's more or less the same, and then a binomial 4k for choose k, and then here we can write up arrow 2 for squaring it, multiply by k factorial, multiply by x to the k, we get the same again. Okay, so now if we're going to do the version with the full pack, then that would have then the relevant board would have 13 of these 4x4 blocks instead of just 4 of them. So we need to calculate r to the p to the power 13. So that's this rather big polynomial here, and then we have to do again this alternating sum things. You get minus 1 to the k times now it's going to be 52 minus k factorial multiplied by the coefficient of x to the k and r, and we're doing this sum now from k is 0 to 52. And so we get the even bigger number than we had before, and in Maple the notation eval fn to write this in scientific notation is 1.3 times 10 to the 66. But if we want the probability, then we have to divide that by 52 factorial, and this gives us 0.016, or about 1.6% as the probability of completing a game of Snap with a full pack.